Hello friends, this is Abhishek once again, and today we shall be discussing about Faraday Cage. And I hope and I'm sure we'll go through the entire video, and you'll really like it because it goes into the depth of understanding. And let's get started. So I have chosen a hollow conductor. Uh, The conductor is chosen irregular in shape so that it can be generalized for any enclosures, conductive enclosures. And let's start with the static case, electrostatic case, or time invariant case. Fine, and I've chosen three charges, 3-point charges placed at some distances from the conductor. And initially the conducting hollow conductor was neutral, so whatever charge gets induced here, q1, q2, q3 and q4, will be such that the sum of all these charges is 0. I have chosen the Gaussian surface external to the conducting sphere, or the conducting shell, or the hollow conductor you can say. Now what about the surface charge density? Now the first thing you need to understand is whenever you introduce these charges here, these charges induced will initially distribute themselves. They will shift here and there in the outer surface and the inner surface in such a way that finally the forces stabilize their movement. That means there no more movement occurs. Now in this stage I can say that the electric field inside or within the conductor is 0, and if I draw a small closed path here and apply closed line integral of the electric field, since the curl of electric field is 0 for time invariant case, E dot dl will be 0 for this closed path. So I can arrive at this condition, E10 equal to, or the tangential component of electric field at the surface is 0. In other words, this conductor is equipotential. The field lines at the surface will be normal, and there is no current anywhere, and electrostatic situation has been realized. And what about any Gaussian surface chosen inside or within the conductor, I should say? It will enclose charges q3 plus q4, q3 plus q4, and because electric field intensity is 0 inside the conductor, d dot ds will be equal to 0, which is equal to q3 plus q4. Fine. So now the thing is, what about the field in the inner region of the shell? In this part of the shell, if I choose a Gaussian surface like this, and if I assume that field lines exist, these field lines after taking dot product is equal to 0, closed surface integral is equal to 0, because the charge enclosed is 0. Now the electric field lines, if it exists, will be either directed towards the center or away from the center, right? But the dot product over the closed surface integral is 0, which is possible only if d is 0. That means our supposition or our assumption is wrong. D has to be 0 inside everywhere within this region. So this is how we can explain Faraday's Faraday cage principle, that electric field inside a hollow conductor or a conducting body is 0. Now this has to be proved for time varying case as well. Now in case of time varying fields, the case becomes complicated. Why? Because See, these are the sources producing electromagnetic fields, and they are all time varying. We'll have DC currents, we may have static charges, we may have time varying magnetic fields, electric fields, and due to this some complexities will be introduced. Let us see the complexities. So the things which need to be catered now is the displacement current. See, since electric field exists and it's varying with time, del D by del T this is not equal to 0. So displacement current will exist in the outer region. Conduction current may also exist. For example, in this demonstration of Faraday cage, this Tesla coil generates very high voltage, and this breaks down. This causes dielectric breakdown of the medium, and there is a current path up to the cage. As you can see, we shall prove that inside electromagnetic field is 0, but up to the cage there is a path, and this current then flows through the conductors of the shell or the cage, and it's finally grounded. So we may have conduction currents that cannot be ruled out because we are no longer in the electrostatic case. We may or may not have conduction currents, but displacement current will be always there because we are dealing with time varying case. Fine. So we'll have time varying charge distributions. Okay, now the thing is how to design, means what should be the design of this cage. See, the most important thing is that we shall prove is whatever may be the enclosure, whether it is in the form of cage, whether it's in the form of a completely solid shell. The important thing is the field inside. The field inside will be 0. Inside means I am talking about the interior of the shell, right? Now, how to design depends on the application. For example, in this case, this is a hotline maintenance worker. Now, he works over an energized line, and he has to wear a protective suit which is made of stainless steel threads and insulating material. Now remember, realize this concept that this, although this suit is conducting, see, he is working over the line, and as you can see, although this suit is conductive, it has got sufficient resistance as well. So in this design, the suit is made up of stainless steel threads and insulating material. So what it does is, although it forms a Faraday cage, it ensures that his suit resistance is high enough so that no current flows through his body. Means through, I should not say through his body, means through the or over the surface of his suit. So the current continues to flow normally, and there is no current flowing through his suit or any part of his body, because inside electromagnetic inside he is shielded definitely, but and over the surface of his suit there is no current, and his suit has sufficient resistance so that the normal current path is not disturbed, because current always flows through the lowest resistance path. Now the thing is, we have to prove this fact that electromagnetic field inside the hollow conductor is zero in case of time varying. For electrostatic, we have already proved that electric field is zero, but we have to do this also for time varying case. Now, as I have said, that in the thickness region we may have currents, definitely, because it's a time varying case. We may have non-zero electric fields, non-zero current density, non-zero displacement current as well, right? Fine. Now for now the thing is how to realize this equipotential case. How can you say that the conductor is equipotential? Now to realize this fact, let us see this example. In this example, this is a cage, metallic cage, so it's a Faraday cage, I should say, and the person inside is shielded from the electromagnetic fields outside, right? Now since it's a cage like structure, the first thing that it will do is it will the conductors are conductive enough to give a path to the flow of current, and also what it does is the flow of to give a path to the flow of current. To this current means this lightning jolt strikes here and it gives a path to the flow of the lightning current, right? It gives a path to the flow of this lightning current. Now when we have cage like structure as shown here, what it will do is it will distribute this current into smaller current elements, isn't it? Smaller current elements, and what this will do is we won't have a high potential difference between any 2 points because the current is getting distributed into smaller paths, isn't it? So at any 2 points, between any 2 points, the potential difference won't be that much. So it is almost a equipotential. Try to understand this. Say if I ground this point and if I ground this point also, 2 grounding points, and this lightning jolt strikes here. So what will happen? This current will distribute in smaller elements because it is a cage like structure, and since each distributed current will pass through and it will give a very small drop, potential drop between any 2 points, isn't it? So my voltage difference, potential difference between any 2 points is very small, so I can say that more or less it's a equipotential surface. So by ensuring a cage like structure, I'm able to make it equipotential. Excuse me. Now let us see the other case. In this, the worker, as I've already said, this suit is made up of stainless steel threads and insulating material, and what he does is, just when he is about to get down or when he is about to reach the transmission line, he first charges his body, the helicopter, the pilot, to the potential of the charge line, energized line, right? So since he charges up to that potential, once he gets down over the line, he is safe. He also utilizes a rod as he approaches the line. This rod ensures that this rod gives a flow of the charging current to flow through his body and to the helicopter, so that he is charged and up to that potential, right? So they are charged up to that potential, and once he gets down, he again uses the rod. The helicopter sets off from here. He gradually detaches the rod from the helicopter, so that whatever potential difference is being introduced is guided through this rod, right? Is guided through this rod. Now, in this case, his suit is made up of stainless steel threads and insulating material, which ensures that this is metallic suit, no doubt, but it has got insulating material also, so it will give some resistance to the flow of normal current. Normal current cannot pass through it, right? Normal current cannot pass through it because the least resistance path has to be followed. So in this way, in this design is little bit different. Okay, now whatever be the case, the thing which we have understood is that the cage or the structure, metallic structure that we are using it's more or less equipotential, right? More or less equipotential. So if you are using it in the form of a cage, then also we are able to make it equipotential. And if you are using it in the form of protective suit, and then also the design is such that it is ensuring equipotential. So when it is equipotential, the electric field lines will be normal. Say the electric field lines which will be at the boundary of conductor air, boundary outside, will be normal, and the electric field lines in the inner region will also be normal if it existed. See, we'll prove that these fields do not exist, these field lines do not exist. Now, since the strongest point now we have is that the conductor is equipotential, and if I draw a Gaussian surface here, again with the same analogy that we have already proved a little while ago, we can show that the surface integral, closed surface integral of these field lines, which are either directed towards the center or directed away from the center, will always be zero. That means the electric field has to be zero, isn't it? Electric field has to be zero at all points inside. So once the electric field is zero, we are in a position to prove that the magnetic field is also zero. But how? So to prove this, we shall introduce Poynting theorem. Now the Poynting theorem says that the energy transfer through a Gaussian surface is equal to the sum of ohmic power, I should say the power balance, the ohmic power, the magnetic energy stored, and the electric field energy stored. So all terms having E will be zero. So we are left with this condition, volumetric integral of d square by 2 nu naught dV is equal to 0, which implies magnetic flux density is 0 at all points inside in the interior region of the shell. So whatever may be the case outside, electric and magnetic fields inside in the interior region of the shell is always 0. The important thing is we need to ensure a cage-like structure so that it is equipotential, and if you can't manage a cage-like structure, then also, like for example in the case of a vehicle which is parked somewhere, and there is a lightning outside. It is said that we are safe inside the vehicle. This is uh, because it is because the metallic enclosure shields electromagnetic fields which are outside. So for a perfect neutralization of electromagnetic fields, we have to ensure that in the application of, say, uh, Tesla coil of death, which Tesla cage of death, I should say, which I've already shown here. It has to be in the form of a cage with say a very highly conductive material like that of copper, made of highly conductive material, right? And that's all. We have made the electric and magnetic fields. We have proved that the electric and magnetic fields inside a conducting shell is zero. And a very important application is this one, hotline maintenance. It's a very interesting application because electrician is able to work on an energized line. Other applications may be like metallic shielding of cables, and even ATM card holder is also a Faraday cage. Metallic ATM card holder is a Faraday cage. So it has got large number of applications, and it's a very interesting result and a very useful result. And I hope this video was useful.